Hello. In today's session, we're going to cover what non-engineers need to know about concrete masonry. My name is Sam Rubenzer. I'm the founder of Force Consulting and the managing director. I'm a licensed structural engineer in the state of Illinois and a professional engineer in a lot of Midwestern states. I have my engineering degree from the University of Minnesota. I have an MBA from Marquette University. We've been working with the masonry industry for about 15 years as consultants to different coalitions. We also have been working with the masonry industry in software tools for about 20 years since my days at Bentley Systems. For this presentation, really what we want to do is we want to cover for non-engineers what some of the important items for structural masonry design and construction that we're teaching engineers today. We really want to kind of rise all boats with the tide, and so we really want everybody to understand some of the different important items that we are teaching structural engineers about current and modern practices for structural masonry. So looking at different best practices and looking at some different case studies that we have to provide efficient and cost savings and sustainable solutions, but also being highly effective designs as well. Really quick on some systems overview, really kind of looking at structural masonry. Some advantages over other materials is certainly has the versatility and field adjustable nature of masonry construction. Obviously, you have non-combustible. You have equivalent strength to concrete with a lot less material. So less concrete required with the partial grouting, less reinforcement because of the blocks coming to the site already cured. So a lot less shrinkage forces, and certainly the temperature loads because of the less material would be less as well. So we have higher strength and stiffness than a lot of other alternative stud solutions. So really kind of what we're looking at today is some things that clarify in terms of strength. Oftentimes we see designers assuming lower strength than what we actually have in reality, so we'll cover that really quickly. Look at some wall selection, some tools for wall selection to make sure that we have an efficient and as thin as possible masonry solution. Certainly thicker solutions could work too, but also wouldn't be all that efficient and maybe not a good responsible use of materials. Look at some different reinforcement, splices, grout placement, movement joints, and really kind of movement joints affect the overall structural design, but we really want to give everybody a little bit of some tips on where movement joints should go and who the responsible parties would be. And then just some of the different costs of cold weather construction. Oftentimes it's assumed to be a lot higher than it is. Also look at other items in terms of like prefabrication of masonry and stuff like that, that can really kind of mitigate what some of the costs would be due to cold weather, because they can be built maybe in a prefabrication warehouse facility. Where to use structural masonry, and oftentimes when we look at what structural masonry can do, there's a lot of different places that you can use structural masonry. Certainly for the foundations for buildings, again, another great way to use a lot less material to do the same exact things as concrete is to use masonry foundations for both basement walls or stem or frost walls. Shaft walls for stair and elevators, certainly out of masonry, can be a very efficient use of materials. But then those walls also can be firewalls, shear walls, bearing walls. We also have masonry partition walls without a lot of structural function, but again, a durable masonry partition wall certainly has a lot of benefits to them. And then looking at some possibilities for structural veneer walls that we could utilize. Usually when you have masonry, you don't have necessarily an all masonry building. Masonry is going to be a part of the solution. Primary framing systems could be wood, maybe cold form steel or structural steel, concrete with PT slabs, precast, and also masonry bearing wall buildings. But again, that's going to have to be a mixed material system with other materials framing for the floor systems. So again, if we have these different types of buildings, where can we use masonry? You can certainly use foundation walls. When you have any wood, cold form, steel buildings, generally if you have a concrete building, though, you're obviously going to use a concrete foundation wall or basement wall. But then again, if you have precast or if you have a masonry bearing wall building, using masonry in those situations works pretty well. Shaft and elevator walls, really you can be using that for, again, a variety of different types of building from primary framing systems. And firewalls, really you could use masonry kind of throughout any different type of framing system. You get into hybrid walls. Hybrid walls would be where we have maybe steel or concrete main framing systems, and you can use masonry as kind of the infill element in some of those frames, and connecting those elements creates a hybrid frame. So it can be a very good solution. For interior bearing walls, partition walls, again, for steel, concrete, precast, you certainly can use masonry for those different types of buildings. And then certainly for exterior buildings, certainly with a veneer, you'd be able to use masonry with all the different primary framing systems. But again, exterior non-load-bearing walls or bearing walls, there's a variety of different ways. So really kind of looking at the overall map here, you can see masonry can be a small or a large part of the solution for really any of the different types of building systems that we have today. Masonry wall types, we have load-bearing walls, which could be a single withe wall, cavity wall, or some proprietary system. You have masonry veneers, which could be anchored or a structural veneer. We also had adhered veneer, but then we also have prefabricated masonry. We're seeing more and more prefabricated masonry being selected and chosen for a variety of different reasons. Post-tension masonry, which can be used. We have partition walls, 6 and 8 inch unreinforced, have a lot of potential, but then we also have hybrid structures, again with the steel or concrete frame and masonry infill. So structural load bearing, cavity wall for masonry and veneer, that's going to be certainly one of the most common systems. Single withe wall, there's still a place for single withe masonry. It's not in every building solution, but we certainly have plenty of maybe auto repair shops or car washes or different types of buildings that just have more of an industrial finish, but still require the little bit of aesthetics with masonry and some of the overall usage that you can use. So single withe still has a place, but then we also have some proprietary systems with some integrated installations with some of these systems, and there's a variety of them that we'd be happy to discuss to anybody that would be interested. For masonry veneers, certainly an anchored full bed veneer is going to be very common solution for design, but you could also have a structural veneer where you have the veneer that actually could be reinforced, maybe vertically or horizontally, depending on the units that are selected. And then you also have the adhered veneer that's going to just be applied to the backup wall. Hybrid masonry structures is really going to be, again, looking at concrete. Maybe a post-tension concrete could be a really good example here, where you'd have a post-tension concrete building with post-tension concrete slabs, and then you have concrete columns. Really putting in walls too early in the post-tension concrete buildings do cause a lot of difficulties. So really the natural solution for this could be adding the walls later, and that obviously fits masonry pretty well. We can do the concrete columns and post-tension slab, and masonry infill wall is a hybrid system. We also have the steel frames with the masonry infill. Again, oftentimes it's going to be more of a contractor preference, where he wants to go up with all of the steel at once, so he can not, say, go back and forth between trades. Certainly that can be an option for some designs. But again, the hybrid aspect of it is then connecting what we maybe want with the masonry for durability and all different kinds of architectural reasons to that steel frame to provide some lateral resistance and maybe load-bearing gravity resistance as well. There's other things that we're talking about now more with masonry with, say, some high-end ideas where we're prefabricating masonry. Could be lintels, could be entire shaft walls. And in fact, we actually did an entire building out of prefabricated masonry design. So all things that we can certainly talk about and look into more. Some of the things that we're talking about in terms of, again, masonry strengths. Again, we're not going to get too into the weeds of all the different aspects of strength, but if you do have masonry design, I think it's important for all of us, if we're not engineers, to be able to kind of check and verify and make sure that we're using materials that are going to give us, again, the most efficient solution. So really, if you look at masonry units, the block ASTM C90 is going to be a pretty straightforward way to understand the material by looking at the specification for it. But really, the code is going to give us a really good guide to what the actual overall strength of material would be. So it's going to be based on, say, the TMS 402-602 code book. Within that code, there's going to be a table. This table is really kind of written for contractors. So as a designer maybe specifies an F''M, what the contractor then needs to do is go find the materials that would fit that F''M. So again, looking at this table from a contractor's perspective, they're going to start with the information on the left as the design strength that they need to meet. And then they're going to go find the materials. Again, if they have type M or S mortar, then they know that they have to find unit strengths of the values in the table. Or if they have type N mortar that they would like to use, you can see the higher strengths of units that they would need to find for finding that very same strength. For an engineering perspective, what I like to do is I like to flip these values around, so exact same values, but if I move them around a little bit, again, as engineers, we're looking at it maybe from the perspective of what units are available in a particular area. I know as I do designs, I'm going to have different parts of the country that I might be designing in. I should be understanding what some of the different strengths would be for the units in different parts of the country. I know I'm going to use a type S mortar. We'll talk about that in a little bit, but since I'm a structural engineer, I like to use type S mortar. It's got some really good properties structurally that we want to use. So I know what the units are. I know I'm going to specify type S mortar, and then I'm going to get the overall F''M strength on the far right column. So again, just the same table, just the values reoriented a little bit more for an engineer. Speaking of mortar, the different types of mortar that we have, obviously mortar is going to be the other aesthetic to the wall. We have certainly the block and block textures, block colors that we want to use, but certainly the mortar color is going to be of importance as well, how it kind of blends with the overall units that we have. But from an engineering perspective, really mortar is going to be kind of that glue that holds the units together. It's going to have some strength properties, but we really have to make sure that we focus in and understand strength a little bit. And so I'm going to give you some values, a few values about the different types of mortar. Again, the most common types of mortar are going to be type M, type S, and type N. You can see for a mortar-only compressive test that can be done for the mortar, you can see some values that are up there for these different types of mortar. What's really, really important to recognize is those values are not the F''M of the wall. Those values are for just the mortar-only compressive tests. So when we test mortar, the difference is when we test mortar, we're going to just take it as a sample. We're going to take a cube of this mortar. It's going to have a high water to cement ratio, and it's also going to have an aspect ratio of kind of 1-to-1 in terms of the mortar cube that gets created. So when that gets tested, what we find is that the actual strength of the mortar in that test is going to be less than if I put mortar in the wall. So why is that? So when I put mortar in the wall, the actual water is going to wick away from the mortar and into the unit. So it's going to have a lower water to cement ratio. And so anybody with that engineering background is going to know when I have a lower water to cement ratio, our strength actually goes up. We also know that when mortar is placed within a wall, it has an aspect ratio, kind of the width to the height, of around 3-to-1. So that's going to, again, yield a much stronger mortar. So the exact same mortar, when I test it in a mortar compressive test, is going to give me a lower value than the exact same mortar that I use within a masonry wall. So it's really important to recognize different types of mortar have two sets of values really that they would be associated with. Just the mortar compressive test, which is not a strength that we need to design to. It's just defining the properties of that mortar. But the overall assembly strength is always going to be greater than those mortar-only compressive strengths. So again, if I look at the different types of mortar, again, I said the going from right to left, from type N to S to M, we know the mortar compressive strength goes up, but that's really not an important value, and we really don't want to focus on that too much. We know that when we have the actual table gives us the two mortars, type M and type S, to be equivalent to one another in terms of the overall assembly strength. So again, type M is 0% stronger than type S when we look at the overall assembly strength for the wall. If we do go to type N, we know that we have a 10 to 15% reduction in the overall strength of the assembly. So it does make a difference what mortar you choose, but generally type S is a really nice mortar. And the reason why I say that is the workability, ease of construction. is actually kind of the inverse of the overall mortar strength. So if I go from left now to right, type M mortar is going to be the hardest to work with. Really doesn't have a very good workability or ease of construction. And so a lot of mason contractors prefer not to use type M mortar. So really, I think a good way to remember this is, again, maybe type S for structural, which is a really good way to remember. S is going to have a lot of the good properties that you need for structural design, but it's also going to be mason friendly in terms of construction. So again, this is all going to be within the table, so that's why we selected the type S mortar there. So we know what the units are, we know what the type S mortar is, and then we can get the overall strength of masonry F''M. The last concrete material that we're going to be looking at here is going to be grout. Again, it's going to have an ASTM associated with it. Grout, really the only important part of grout is it's at least as strong as my F''M or 2000 PSI. So we're always going to meet the 2000, but our F''M can be a little bit higher. So we want to make sure that our grout is at least as strong as F''M. So again, if I look at the same chart, we have the units, we specify the mortar, we know what our F''M is, and then just making sure that our grout is compatible with the rest of the system, we want to make sure that our grout is at least equal to, if not greater than, the overall strength of the wall. So that's really our three different types of concrete that we specify within the structural world. Then we look at reinforcement. Why reinforcement? Masonry is really good in compression. Reinforcement is good in tension. So the two of them make a very good, strong complementary materials within a wall. And when we're specifying these different items, we have the different types of concrete elements. Again, the block, grout, and mortar. I think it's really important that we don't just specify F''M as equal to a certain strength. We really want to get to giving the overall assembly strength and then defining the different elements that make up that strength of mortar. So, for example, if I looked at an F''M of 2500, we know that we have units that would have to be a little bit higher with type S mortar to give us an F''M of 2500. So all going back to the tables within the TMS code. It is possible to use two different types of mortars. Two different types of masonry strengths on the same project. In fact, I was just asked this question yesterday, and we just had a dialogue with an engineer that if you look at the unit strength method, that does cap off at 3,000, the table that I had before. But really, the code allows you to go to a strength of masonry up to 4,000 PSI within strength design provisions. So really, you have between, say, 2,000 to 3,000 with the tables in the code, but then you can go all the way up to 4,000 if you had a higher load demand situation, maybe like the building that we see on the right, where we have 10 to 12 story buildings. Certainly the load demand gets a little bit higher, and maybe we want to consider a higher strength block. And certainly block companies are happy to make those higher strength block as long as they have a little bit of time to make this new unit and test the unit to make sure that we're meeting the overall prism, because then we have to get into prism strength testing, and that's going to be really, really important to make sure that we have that done in a timely fashion before the project needs to get started. So the other thing to realize is people talk about, higher strength masonry is definitely going to lead to a lot higher cost, and you have to remember that good portion of the overall cost for masonry is going to be labor. So labor is going to be equivalent. It doesn't really care what the actual strength of the units are. So there would be a premium on the units, but there's generally not going to be a premium on really much of a premium at all on the mortar or the grout. It's really just going to be on the units. We're going to have a little bit of a small cost in testing, but then we get to the labor, and that's going to be equivalent regardless of the strength. So sometimes using higher strength masonry can actually result in maybe some cost savings because if you use, say, standard strengths or minimum strengths, we might have to use a lot larger units. So the actual labor cost might go up quite a bit. And so it's really kind of a balancing act that masons and mason contractors do have to entertain. So F''M is important. We look at different design strengths and how it can affect different wall designs, both bearing walls, non-load bearing walls, shear walls, but then certainly the lintels within those walls. That gets affected pretty strongly by the strength of masonry. Columns and pilasters, lap lengths get shorter when we use a higher strength of masonry. connections to masonry become a lot more efficient. So it is a really important value to understand for your project. Again, weighing some of the pluses and minuses for what strength of masonry we want to use, what's readily available, and certainly using a strength that makes sense for your project. We have a nice little paper here that summarizes all that we just talked about in terms of the overall strength of materials, why we would specify different values for design. Next thing to look at and think about is we look at the overall wall thicknesses and reinforcement that we want to choose for a project. Again, we have masonry that comprised of a lot of different types of materials, from the block to the mortar to the grout. We have reinforcement. We have vertical reinforcement that we talked about, works well with the tension in the reinforcement and the compression in the masonry. Is very complementary to one another. That's great. But then we also have other types of reinforcement, like horizontal reinforcement. And then we have other types of material needed for control joints. And control joints are basically predetermined cracks within the wall to relieve some stresses. So where do we want to put those, and how does that all come into play? So we'll talk about that now in a little bit. So cavity wall systems, when we have a cavity wall system, we know that we have all the different elements that make up the structural wall. But then we have all kinds of other components that we have in here for architectural purposes. We have, air and water barriers. We have venting that we want to choose. We have maybe a different type of mortar in a veneer versus the backup wall. We have different joints that we maybe want to select in the veneer versus the backup wall. So it's really important to understand all the different options and all the different components that make up a successful, high-performing masonry wall system. So if we're going to talk about walls, it's really important to kind of look at what does the code consider a wall. A wall is going to be something that's 3 times longer than it is thick. So if it's an 8-inch thick wall, we have something that would have to be at least 24 inches long, 12 inches thick, 36 inches long. You kind of see the trend. The other thing about masonry is what can we do in terms of reinforcement. Really, if we look at 4-inch masonry, which is available, 4-inch concrete units aren't able to be reinforced based on how they create and make those elements. Really doesn't have a core that's able to be reinforced reliably. So we typically would say a 4-inch concrete masonry is not able to be reinforced. 4-inch clay masonry would be able to be reinforced. 6/8 and 10s are commonly available for both concrete and clay. And if you get to the thicker units, 12 inches and 16 inches, really you're going to be primarily talking about concrete masonry at that time. I think it's also really important to look at some of the different height to thickness ratios. In the past, with empirical methods, height to thickness ratios were a lot smaller, but now we use allowable stress design, strength design. We use engineered methods that give us a higher height to thickness ratio, so that's basically thinner walls. And here we developed a chart that we thought would be pretty useful for designers. We can see what the typical height would be. So if I look at the chart on the right, every place that the color gets very dark, that would be what I would call kind of the sweet spot for that wall thickness. And so again, if we go above or below that sweet spot, what we're typically looking at is something that maybe isn't necessarily going to be cost effective for that thickness. So again, if I had an 8-inch wall, I can see that it goes from 20 to 33 feet. Is a 30-foot tall 8-inch wall going to be effective? Well, if I look at the chart, I can see that maybe 30-foot tall wall might fit better with a 10 or 12 inch design. So again, the chart is really kind of to give a range of solutions. Obviously, everything needs to be designed, but if we're choosing a preliminary thickness, maybe a chart could be pretty useful. We know that we can do some of these taller designs. Again, we look at what we can do with 8-inch masonry. We know we can go about 24 feet with lightly reinforced. We can go up to 36 feet high. If we get heavily reinforced, we know similar things for 12-inch masonry. We can easily go 30 feet, but we even can go to 50-some feet high with 12-inch masonry design. So here you can see a top of wall in this school that was based on 12-inch masonry going over 50 feet tall. One of the well-known structural engineers, David Biggs, often talks about what we're able to do with masonry walls as a result of misconceptions, misunderstandings, lack of knowledge. Masonry is not being used to its full capacity to build tall walls, and I think that's certainly the situation. We definitely look at masonry and don't necessarily understand its full capacities and more reasonable height to thickness ratios. So I certainly think a lot of study could be done here to really kind of show what different options you have for different heights of walls. And to carry it a little bit further, just talking about the overall costs. Costs of walls, again, if I could talk about, an 8-inch wall can go from, again, the 20 to 33 feet. But again, where does the cost start to tail off for 8-inch walls? We know we get a little bit taller. I can go to maybe a 10 or a 12-inch wall and have it be more cost effective than the 8-inch. But conversely, if I looked at, say, a 10-foot tall wall, I know that I could do it with 8, 10s, or 12s, but I can see that I have a 10% premium that I would pay to use 12-inch masonry in that situation. So again, it's really important to understand cost. This cost chart was developed for the areas that I work in, but there's certainly, maybe other charts that would need to be developed in different parts of the country based on typical loads, typical strengths that you have. But I think it's a really good chart to have and have available for choosing thickness of masonry walls. Again, looking at masonry, firewalls are going to be a really important component to the overall solutions that you can choose for a building. And again, this really kind of crosses all the different primary framing systems. Using masonry for firewalls certainly can work very well. Masonry firewalls and structural masonry, really you have different wall assemblies. You don't have to have all of your masonry elements be solid grouted. You can have equivalent thicknesses that you can utilize based on the masonry assemblies. You can look at filling the cells with loose fill. You can look at multi-width wall assemblies and see what the overall fire rating would be. Obviously, looking at masonry lintels, masonry columns is going to be a preferred solution for a firewall, just because certainly because of the increased fire resistance of those elements. Again, within the NCMA charts that we use for design, NCMA now converting over to CMHA, but this tech guide is still available where you can see what the equivalent thicknesses would be and how that would rate for different fire assemblies. Again, equivalent thickness is going to be a really important part of the overall design. You can see that based on solid grouted units, the increased equivalent thickness, but just based on maybe 75% of the unit there, we can see that the equivalent thickness may be more than what you need for the designs that you need for a firewall. I can expand that table and certainly kind of draw out all kinds of different types of equivalent effective thicknesses for different wall thicknesses and different grouting schemes that you would use for your designs. Again, looking at firewalls and reinforced concrete masonry columns, seeing what the different fire rating would be for the minimum dimensions of masonry columns, and then a very similar respect to the reinforced concrete masonry lintels, what the cover would need to be to achieve different fire ratings for their designs. Shear walls and partition walls are a really important aspect of what we do for structural designs. Looking at shear walls, there's a lot of different definitions for shear walls. And again, I'm not going to get too into the weeds of all the different specifics here for all the non-engineers, but recognize that when we have a shear wall, we have a lot of different criteria that can come into play. Just looking at the seismic regions, we have different types of reinforced masonry shear walls. In fact, within the code, if I was to summarize all the different requirements, you can see for an ordinary reinforced wall, we have vertical reinforcement requirements, horizontal reinforcement requirements at the top and bottom of openings, and then at each side of the openings, we have reinforcement requirements at the top of the walls. And then if we go to the next reinforced masonry shear wall category, intermediate reinforced walls, then we can see we also have a vertical reinforcement limitation to be not more than 48 inches on center. And I think that should be a little bit of raising a little bit of awareness. It's not until we get to an intermediate reinforced masonry shear wall that we need vertical reinforcement at 48 inches on center. So if we had an ordinary reinforced masonry shear wall, or if we have another type of wall like a partition wall, I don't need to have reinforcement at that spacing. I can certainly go further than 48 inches on center to have a wall for a partition wall, and maybe it would even be able to be unreinforced for a partition wall. So we have to recognize that. We also kind of point to the reinforcement at the top of the walls. It's just a shear wall provision. We don't need to have bar reinforcement at the top of partition walls. It's another place that we could certainly have significant savings if we eliminated that top of wall bond beam for partition walls, because partition walls are certainly going to be walls without interior structural function. So it really is going to be just a wall that it needs to hold itself up. It really doesn't have really any significant loads on unless it's in a higher seismic zone. So in fact, we create some tables to show that many of the partition walls can be unreinforced for seismic design categories A and B. So it's certainly a much less than reinforcement at 48 inches on center. They can be unreinforced, and when they do need to start being reinforced, I can go all the way up to 10 feet on center for the overall reinforcement needed. So in fact, if I go one more step, if I go to seismic design category C, I can see that most of the chart here for the different thicknesses and different wall heights is going to be reinforcement at 10 feet on center. And it's not until I go to seismic design category D when we, again, would have probably intermediate reinforced shear walls and partition walls that need to have reinforcement at 48 inches on center. So we're going to have more load demand, more inertia force due to the seismic activity that you would have in seismic design category D, but that's going to be, again, a small percentage of the overall country. So really with partition walls, we're looking at how we can simplify, how we can pull out some of the reinforcement that is somehow snuck into the designs, the typical designs for partition walls. So we really want to simplify, take out any horizontal reinforcement, especially if you don't need it in lower seismic design categories A, B, C, and D. Quite possibly you don't need the top of wall bond beam, so let's also pull that one out of there. We don't need the vertical reinforcement at 48 inches on center, so let's look at reducing that as well. And maybe we can also simplify those top and bottom connections, just putting the connections in dowels, maybe where we need them. Look at some different details that can give us some different opportunities for connecting at the top of the wall. There's also PTA connections that are gaining a little bit of traction. Again, anchors that allow the wall to slip in plane. So it's not going to be a shear wall. Allow it to slip in plane relative to the structure around it, but also then not load the wall with any unintended vertical forces. So different types of connections that you can have at the top, different types of connections that you have at the bottom. Again, a particular look at the doweling that we use for partition walls. It really doesn't need to have significant dowels if it doesn't have any other function other than holding itself up. So again, looking at trying to get partition walls to be the most cost effective really does require us to start to look at taking advantage of some of these efficiencies and designs for partition walls. It's going to be a really important part of keeping those walls affordable. One of the first things that we were challenged with when we worked with the different structural coalitions was, a lot of partition walls, masonry partition walls, were getting valued engineered out of projects. But in fact, what it should have been was valued engineered to a standard of partition walls that's needed for the design loads. And so really kind of the value engineering towards an efficient masonry wall first. And then, certainly if that still is too costly, then looking to other lighter materials, less durable materials and stuff like that. But we certainly need to know what the most efficient partition wall is in masonry before we consider value engineering it out. Masonry foundations. Masonry foundations is another really great topic. Masonry foundations, the biggest part about it is it's going to be a lot less material. It's going to be some consistency with the walls above, especially if we have a cavity wall or a masonry wall above. So it's certainly going to be less material, less cost, and a lower carbon footprint. And I have often said that if you are at all serious about sustainability, lowering carbon footprints of the buildings, and you haven't used masonry foundation walls, I just don't think you're that serious, because this is a place where you can significantly improve sustainability for a building and significantly lower the carbon footprint for your design. So masonry foundations are certainly something that we can do. Again, the CMHA tech guides give us some really good guides and steps for the units that would be needed types of mortar that we should use below grade, vertical reinforcement, joint reinforcement, making sure that we put in a solid top course. We don't have to have solid grouting in the basement walls or in the foundation walls, but we definitely do want to have a solid top course for a variety of different reasons. We want to have waterproofing on the outside. People talk about masonry being more porous. I'm like, well, it's not porous when we put waterproofing on it. So we know that water's not getting through the waterproofing, and so then it becomes a moot point about the porosity, so to speak, of the masonry elements. So the biggest thing with any foundation walls is making sure that you have good site grading and sloping away from the building, and a good drainage system and drain material and drain tile that's used. So all of those things are going to be important regardless of the material used for the foundations, but it's even more important for our masonry design. So a tech guide here gives us some really good steps for having a successful masonry basement wall. Again, but looking at even stem walls, there's really no need to grout the wall below grade. We want to have that top of wall bond beam, but we certainly don't need to look at having anything beyond that reinforcement or that grout being used for design. The top of wall bond beam becomes even more important when we start to transition wall thicknesses, making sure that we have a nice even shelf for the different thickness of materials that could be above. And as that cavity wall gets even thicker, again, making sure that we have the ability to transition all the different elements. We have a bond beam to close off the top, so it's a sealed up system. If we need waterproofing, we can certainly provide that here in this design as well to keep everything nice and dry. But again, a good site draining and drain tile and all of that's going to be important for your foundation walls as well. So again, masonry walls below grade provides a really simple way to insulate and waterproof. Here you can see where you can also take the cavity all the way down. You can use masonry underneath the veneer elements, and you can put insulation all the way down to the footing. And so again, there's a variety of different things you can do with a masonry foundation in a variety of ways where you can keep costs down and obviously improve the overall sustainability of your project. So masonry foundations can certainly be achieved with good design, good details, reliable construction. A great way to move forward for projects. Move-in joints, expansion joints, and control joints. Really the most important aspect of this is making sure that we understand that it's the designer's responsibility for movement joints. If designers are not locating them, really they should be selecting a delegated design for their masonry systems. So that's certainly something that we've done here at Forest, become a delegated designer for masonry, and then we're locating the movement joints. But if that's not being selected, really the designers, engineers, and architects have to be locating movement joints. There's going to be some basics that we really need to understand for different movement joints. We have both vertical and horizontal joints. In the veneer, we would need to put vertical joints to prevent cracking. We need, when there's differential support, so we have different types of support conditions, we definitely want to make sure that we have a vertical joint separating two different support conditions. It'd be pretty rare to eliminate the vertical joints in the veneer. Certainly you could provide the reinforcement needed to minimize them, but very, very likely you're going to have some vertical joints in the overall design. The horizontal joints, again, horizontal joints are going to be what we would call shelf angles. Again, sometimes those are needed for the differential movement that you would have between the veneer and the backup. A lot of times the backup systems have some more flexibility than a very rigid and stiff masonry veneer. The purpose is not to relieve. For sometimes we hear the comment about a relief joint or relief angles, and really masonry is way too strong to need to be relieved on 99 out of 100 different types of situations. It really is not something that's necessarily to relieve it. It's got a lot of compressive strength and doesn't need to be relieved. Some cases it can be eliminated. So what are some examples here for, say, a vertical joint? When I talked about differential support, like a part of the veneer could be supported on a shelf angle, part by a foundation that's just going to have some potential movement. So there we would want to put a vertical joint. Again, the horizontal joint For differential movement, that really comes to having a building that might be shrinking. Certainly buildings of certain materials like wood have more movement, more shrinking characteristics. And veneers, that could be, especially if it's a clay veneer, but all kinds of veneers can expand due to thermal loads. And oftentimes you can have this differential. And so if this gets to be 4 or 5 or 6 stories, certainly some of that differential can be pretty substantial. So having horizontal joints would be one option. A second option would be providing veneer connectors that have allowance for some vertical movement and that differential movement. So think of like some slotted connections that allow for that movement to occur. So those are going to be a little bit more costly. So you either have to look at and analyze what that differential movement would be, provide those specialty connectors, or provide horizontal joints for the veneer. Another really quick aside from veneer to structural masonry. If we're looking at structural masonry, sometimes you need vertical joints. Again, maybe it's to isolate a structural element. Sometimes you have a partition wall and you don't want that to, say, frame into a shear wall. Sometimes you have a bearing wall and a non-load bearing wall that you might want to separate by a joint. They're also needed to prevent cracking. Sometimes the walls can get pretty long relative to the overall horizontal reinforcement. Some cases you can eliminate vertical joints. You can eliminate them altogether sometimes for structural masonry designs. Horizontal joints, again, there's really not a situation where we need a horizontal joint in a structural masonry wall. And I feel like we need to say that because we've seen them. We've seen a few of these horizontal joints being utilized. And again, this is maybe somebody misunderstanding what structural masonry can do. And so you can see the real live project. So this is a never, never, never. We don't need to have these horizontal joints. We have more than enough capacity for the masonry to set on the masonry below. Again, vertical joints, isolating, say, a partition wall to a load-bearing or shear wall that could be on the outside. Very different function, very different types of movement, and making sure that we have some allowance for separating those elements. So again, non-shear walls to shear walls could be a good example of maybe putting those joints at the corners. Does keep the walls to be kind of a less complicated element than if we have an L-shaped shear wall that's going to be a little bit more complicated. So movement joints can be used for a variety of different situations for structural design. We also want to make sure that we don't get into this sort of a method where we put in too many joints. This would be what I would call an old-fashioned kind of method of separating out different shear walls to be these rectangular areas. And the reason that I say that is now we have tools. We have finite element analysis software that allows us to minimize those joints, have perforated shear walls. We have good analysis tools that allows us to look at this to see what the overall structural properties would be. So what other things are we looking at from a structural perspective for these walls? Again, we use some of these tech guides. The CMHA tech guides 925 gives us some nice tools to understand different types of joint and horizontal reinforcement schemes that we can design for. So let me show you what I'm talking about. This would be what I would call a typical kind of Midwestern design, or maybe most of the country would utilize this type of design where we have some light joint reinforcement that's utilized, and then a regular spacing of control joints, maybe around 25 feet, 25'4", something like that, or 1.5 times the height, kind of some simple rules that we use. Other options, if you didn't want to use joint reinforcement, you can still use mid-height bond beams and top-of-wall bond beams. That's one way with control joints that you can go. In fact, if you keep going along that thought process, if we add enough bond beams, enough horizontal reinforcement, we can really eliminate the control joints in maybe an elevation. So there might be a variety of reasons why we'd want to do that, but we do have that option. Contractors and designers should have that option that we maybe want to consider. We talk about buildings with a lot of openings a lot of times, and we talk about how control joints, we getting more and more control joints. We're breaking up this elevation. We're getting less and less structural capacity. This might be the perfect situation where we look at, well, let's take this elevation. We know that we already have horizontal reinforcement in our lintels. We know that we have horizontal reinforcement in the sills below the openings. We have joint reinforcement. Once we have a certain balance of horizontal reinforcement to the overall concrete masonry area, we know that we don't have to have movement joints in this elevation, and that's a really, really good option. So I just said something that's kind of a key to making this work, masonry lintels. So let's talk about lintels for a little bit. What are structural engineers looking at from a lintel perspective in structural masonry? We know that we have different material options for lintels. Masonry should be the first option. Steel is somehow still relatively common. Steel within a masonry wall is just going to be creating a lot of complexity for the overall design, creates a lot of cost, and it really does significantly reduce the overall capacity of the structural masonry wall. And that's a really, really important thing to think about. It reduces the capacity, it costs a lot more, and so really why are we introducing this other material within the design? There's also a precast option. I guess let's just start with that one. Precast lintels that work well are going to be looking a little bit like what you see on the image on the right. They look like a really stretched out lintel block with a couple reliefs in the end for vertical reinforcement. These can work just as well as masonry lintels. They have some of the limitations in terms of you have to get them ordered, you have to make sure that they're on site, you have to make sure they're of a precise length, but certainly can work very well for a project. In fact, here you can see a project that I actually specified and used those within the project once I knew the contractor was looking for that design. So again, with this, you don't have any shoring that you need to utilize. You build around the precast lintel, you reinforce as if the lintel's not even there. The vertical reinforcement stays in the first cell. You put reinforcement within the precast concrete element, and off and away you go. And it's a very nice, robust design. Steel lintels, that's going to be the one that I'm going to pick on a little bit more. They're very common. Their scheduling is pretty critical. The corrosion protection is very critical. There's bearing plates, and the bearing plates come with an aesthetic issue. There's thermal bridging. That's certainly a problem. They carry that cold from outside to in or hot from outside to in. But the thermal bridging also does point us to another potential issue of differential movement. When we have that element that's carrying that cold more quickly than, say, the masonry around it, that means we have a steel element that's shrinking and the masonry that's not moving. And so what that happens is, you have differential movement. You have support points then that have to be flexible to that differential movement if that's going to be successful. So it's going to be a costly kind of connection at the supports. And the more complicated part of it is it also has to be a rigid connection at the supports. Anytime that it's used in the, as we see in the image here, when we have a veneer that's sitting on the steel that actually creates a torsional load on the steel element. So now when we get to the end of that steel lintel, we need to have a rigid connection to the masonry around it so that it can transition that torsional load into the wall around it. So in one case, we need a flexible connection. In another case, we need a rigid connection. And really, you have a very costly, complicated element to resolve. And really, they were just chosen for eliminating shoring. So if we can resolve the shoring in a variety of ways, then we really don't need to put in these steel elements that are pretty complicated, very costly to put these in. A lot of potential problems. When I do a project review, these are going to be some of the first ones that I'm going to highlight and identify potential problems that you would have in your masonry design. We're really trying to get away from these type of cracks, probably the most common cracks in a masonry wall, things that could be avoided by just eliminating that steel and allowing it to be just a masonry lintel. So unfortunately, we still see it. We see it on scale. Anytime that we have dock doors or fire stations or a series of openings, we have a lot of potential problems that can occur due to these steel lintels being used in a masonry wall. So the newer method, the better way to do it would be to do masonry lintels, eliminate all the control joints, and then you have a very robust solution. So in fact, we engineers are doing analyses that look like this, where we put the load on the element, we look and see what the stresses are. You can see the solution with all masonry lintels is going to have a lot less stress in the wall, a lot less movement in the wall, all things that are going to be very important. So masonry lintels are going to be, again, fast, economical, match the wall, going to have good fire rating. They're going to have good thermal performance. They're going to be something that can be prefabricated. Here you can see the image in the bottom center is going to be a prefabricated masonry lintel, and that's going to fit within aesthetically the wall that you're building it into, and so that's going to be a very nice match. Masonry lintels can also span 20, 30, 40, even up to 50 feet for the masonry lintel designs. The longer the lintel, the more it makes sense to be masonry. And we looked at that from a cost perspective. And yes, it's going to be difficult to build a 50-foot long masonry lintel, but there really isn't a simple other solution that doesn't cause an immense amount of problems with the overall design. So again, prefabricated masonry lintels are really straightforward elements that we can prefabricate sometimes on site, lift them, set them into place. It really does eliminate the need for shoring. There's other shoring solutions that have came up in the last few years that have been really great time savers from a construction perspective. You can set the shoring, you can build the masonry lintels, you can remove the shoring pretty quickly and reuse it. So it's a very nice options. Here you can see prefabrication though really looks at maybe one span or multiple spans that we can prefabricate all at once and set these lintels in place. So it's a good speed alternative, but it's also a good alternative in terms of a much better, much robust, more robust design. And again, finite element analysis is going to be key to looking at what the different stresses and forces are going to be in these lintels. So we engineers are certainly looking at that and looking at the forces that you're going to have in all areas of the wall, but certainly looking at the areas in a lintel. A lintel is going to be places of high stress concentration. But again, for an elevation like this, I talk about, again, those lintels, those continuous walls, eliminating control joints in an area like this. And that's going to be very good for the shear wall component of it. It's going to be very good for the lintel design. Having a continuous beam is going to be much more robust than individual separate lintels. So all things that are very important for the overall design. Budget and cost considerations, again, looking at some of the different items that we pointed to, looking at masonry foundation walls compared to a concrete foundation wall. Here we can see pretty significant savings for the overall cost for the design. So over 30% savings for the design. Looking at the cost study a little bit further, we can look at a stem wall. We can look at it in terms of less cost that you have with a fully grouted masonry design. But partially grouted is really when we're going to start saving more and more money. So these are some of the different cost studies that we did for this design. We could also look at it for a full basement wall. Again, we have cast in place reinforcement. We have fully grouted masonry. Again, that's going to be even less cost than the cast in place. But then we get to really significant savings and less time when we go to a partially grouted and reinforced masonry foundation wall. Other cost studies that we looked at the lintels, steel lintels versus masonry lintels. You can see all the different masonry options, all the way down to a 48-inch deep. Masonry lintel is going to be more cost effective than just a simple 8-inch steel lintel. So almost every different situation that we looked at as the steel design option being here 40% more than the masonry lintel option. As it gets longer, again, go to 16 feet long, we can see a much larger steel section being used, even more cost, 62% more cost for this design. But I would also say then, even more of a stress concentration that we have at the ends of the steel lintel, more potential for cracking. So we have a more costly solution that has more potential problems. So again, masonry lintels are going to be far and away the best alternative for that design. We do a lot of different cost studies, case studies, sometimes single story buildings where you can see some 15% savings by looking at different thickness of walls, better strength of masonry, better reinforcement utilization within the wall. We look at, again, some firewall designs. Here we saved over $300,000 by using only what we needed for the firewall, using some equivalent thicknesses and understanding what the firewall options would be for masonry. So that was a pretty significant savings for a project. We look at prefabrication options. Here you can see some prefabricated elevator shafts and projects that use the prefabricated elevator shafts. A lot of times with the prefabrication, people are looking at it as, what can you do with masonry versus what you would do with concrete. With masonry, you have a lot of different shape, size variations that you can very quickly explore and build relatively close to when they would be erected on site. So there's not a lot of lead time. There's a lot of flexibility. The cost for the overall prefabrication is usually a break even, might even be a cost gain in terms of materials. But again, in terms of the speed of construction on site, we usually can save those dollars back for the overall project. So we looked at stair studies, we looked at foundation, we looked at lintels. Here you can see stair and elevator shafts, 2 stories tall up to 4 stories tall we looked at compared to cast in place concrete. Certainly less material, so a lower carbon footprint, but also less cost, less time on the project. So again, masonry making a lot of good reasons for utilizing it here in these projects. Last little case study that I want to look at is utilizing masonry walls. This is a small, simple building, but I think it tells a big story. Here we have some masonry stair and elevator shafts. They're very integrated with the diaphragms and the load-bearing systems. What we also had with this project was a designer that chose to use steel moment frames, not recognizing any of the capacity of masonry for the lateral system. So steel from the vertical perspective, but also the lateral perspective. We looked at the initial strength of masonry, what the overall project would have, and reinforcement that it selected. But when we did and redid the analysis, when we actually included all the masonry elements in the finite element analysis, we could see that the moment frames were getting very little force. And the very little force was due to the fact that the masonry shaft walls were going to be a lot stiffer and really do drag out of all the load out of the diaphragms into those very rigid, stiff shaft walls. So, in fact, the very costly moment frames that we had with this project really could have been just resolved with recognizing the full capacity of masonry. And so when I say recognizing the full capacity, we didn't have to change the overall strength of masonry. They already had something that was stronger than what was in the original design, but we needed to add a little bit more reinforcement due to the increased shear load that would be placed. So again, it was a very small cost increase for the masonry that would have saved all of the costs of the moment frames throughout the project. So again, just as a really quick summary, again, what non-engineers need to know about structural masonry is that structural masonry can be very cost effective, fast, durable, energy efficient. We can go a lot taller and thinner. I really do challenge the height to thickness ratios that some people have considered before, utilizing the full strength of materials when we need it for different load bearing or shear wall designs, fully utilizing our masonry elements as much as possible in projects. And again, some just tips for what different typical materials that we're seeing across the country: 2,500 to 3,000, locating movement joints, using full capacities of masonry, using masonry lintels on every design is going to be a huge cost savings. Looking at just the needed material for partition walls, and all of this really kind of boiling down to, and a lot of the masonry can be prefabricated for different types of designs, and when the projects might be built, prefabrication might be a great tool to making and keeping masonry there in the projects. So with that, we do have a lot of papers at masonrystructure.com where you can get a lot of the information that was presented here today. And certainly if you do have any questions from the presentation, you can reach out to me at sam@forceconsulting.com. Thank you.